In this video, I'm going to talk about confidence intervals and how to determine which is the type of confidence interval that you should use for a given problem. Okay, so in order to do so, I'm going to share with you some slides. Okay, so here they are. And the topic that we are going to see today, as I was saying to you, is how to identify which confidence interval should I use for a given problem. First of all, we need to know that in the inference subject, we have seen 4 cases of confidence intervals. The first one should be used when we know the population, when we want to know a confidence interval for the population mean, given that we know the populational variance, okay? That is the populational variance that you see in the formula, it's sigma. This is something that must be done, that must be explicitly said in the statement of the problem, okay? In the statement of the problems, you should find something like the populational variance is equal to 1.5. Okay, so in that case, that it's not the case, a case that you see in real life scenarios, because in real life scenarios you never know the variance, but nevertheless, you can maybe know the variance because you see it in, I don't know, some theory book or in previous studies and so on, and it is enough for you to use this variance. If that is the case, you can use this confidence interval. Remember what is a confidence interval as well. We need to know whether with a given confidence level that it's encoded in the theta value that you see over here, we want to build some kind, a set of intervals that with a certain percentage, they cover the populational mean. So for example, if you are building a 95% confidence interval, then 95 out of 100 confidence intervals are going to cover the populational mean that you are seeing over there, okay? So basically, this is the confidence interval. As a point estimate, you use the sample mean, x hat that you see over here, plus minus the margin of error. The margin of error it's, has 2 different components, the confidence level that you are seeing over here and the inference error. That in this case is the known variance divided with respect to the square root of the sample size. That it's n, and that it's also something that you need to have in the statement. This is the first case. The second case is the same. It's really similar to the first case with the difference that you do not know the variance. The variance of the problem is unknown, okay? You can see over there how the difference between the case 1 and the case 2 is that in the case 1 you have sigma and now you have S. S is the quasivariance, okay? That it's another estimator of the uncertainty of a random variable, but unbiased. So it is the statistic that you are using here. As we have more uncertainty than in the previous case, we do not encode anymore the confidence using a standardized normal distribution, the theta, but in this case, we use a t-student, that it's like a normal distribution, remember, but with wider tails, encoding more uncertainty. And this is the reason why in the confidence level, we have here the t. Remember that the t value should always be given in the statement as well, okay? So difference between number 1 and number 2. In number 2, you do not have the variance. So they need to give you the quasivariance, and you know that you have to use this formula if that is the case. And then we go to cases 3 and 4 that are not supposed to cover the populational mean as in the previous cases, but now we are dealing with a binary variable. So as we are dealing with a binary variable, we have as a statistic of position the proportion. Okay, so the proportion here is this Q, the sample proportion, and we are interested on building confidence intervals that they cover the populational proportion. Okay, that it's this P. So methodologically it's the same as before, but now we are covering the a proportion. We are covering a binary variable instead of a continuous variable. This is the trick to decide whether you are in cases 1 and 2 or 3 or 4. Okay, and you have as point estimate Q, that it's the point estimate, the position of the proportional variable. And as margin of errors, we have this theta value that is the same as in the first case, but now the standard inference, the margin of error has an inference error that it's the variance of a Bernoulli variable q times 1 minus q, where q is the sample proportion divided with respect to the n and everything into a square root. This is something that it's called standard inference. And if in the statement you don't have anything like we want to minimize the risk or whatever of a confidence interval, then you should use this formula regarding a binary variable. But it is also possible, and it is the last confidence interval that we cover in this course, to build a population proportion confidence interval having maximum caution. This is the scenario where you want to minimize the risk. Okay, if risks is something that worries you, then we are going to build the widest proportional interval that we can using this formula. The only difference with respect to case 3 is that the sample proportion that it's inside of the margin of error, you can see here that we do not have Q anymore, we have 0.5. We have substituted it with 0.5 because it is the quantity that maximizes the margin of error for the sample proportion. Okay, so the only difference with respect to case 3 is to substitute the Q for 0.5. So to sum up, maybe the most important slide of these slides that we have seen. How do I know which one to use? Easy, you can follow these steps. Step 1, do we have to make an interval of the mean of a continuous variable or of the proportion of a binary variable? Okay, if it is the continuous variable, like for example, the grades of the exams, the profits of my company, and so on, then we have to choose cases 1 or 2. If instead we are asked for a binary variable, for example, which is the percentage of students that pass statistics, or whether your companies are going to be bankrupt or not, then we are in cases 3 and 4. In the case of continuous variables, that is case of 1 and 2, how do we know the value of the populational, the value of the populational variance? If we know the value of the populational variance, that is sigma, remember, we are in case 1. We need to be given the value of the variance at the theta value. If in other case, if we are not given the populational variance value, in other words, if we do not have sigma, then we are in case 2. We need the value of the quasivariance and the t value. And this is regarding continuous variables. If the statement is telling us something about a binary variable, or if you want to build the confidence intervals for a populational proportion, then you are in cases 3 or 4. In other words, if it is binary, do we need to build an interval with the maximum uncertainty, or in other words, with the minimum risk, or they do not say anything about risk nor uncertainty? If risk is important for us, if we want to build the widest possible interval having a sample size and a confidence level, then we are in the case 4, maximum uncertainty. Okay, and we are not going to use the sample proportion instead of inside of the margin of error, but we are only going to use a value 0.5. And in the contrary, if nothing is said, then we are in case 3. If you follow these rules, if you follow these steps, then it's trivial and it's going to be easy, really easy how to know which confidence interval should I use for every problem. So this is all. I hope that you have liked the video, and if you have some questions, please send me an email. So have a good day.